Okay. Now, let me pause the recording. And our next speaker is Andrzej Sitarz from the oldest Polish university, 1364. And we are very happy to have him speak about quantum symmetries, which is a very big work package because we had an entire thematic research program devoted to quantum symmetries. So this is one of these area of very intense explorations. So Andrzej, the floor is yours. Take it away.
The screen is mine. Thank you very much, Piotr. I hope you can hear me. So sorry for the switch. The good thing is, I mean, I presented something like an overview what's going on and what are the results, you know, and what are the hopes. So that might not be, you know, a very long talk. I mean, but I hope, you know, to certainly not overdo it. So let me just think whether I can. Yeah.
And make it, full screen without all these frames.
Without all these frames, let me just see. Is it visible?
Yes, still we see the frames.
Oh, okay. Let me just turn this to now.
Yeah, but it's very small now.
Okay, that's sorry. So I need to, you know, switch the screens. Okay, this is something. Okay, here. Full screen mode. And is it okay now?
Beautiful. Perfect.
Very good. Very good. Okay. So sorry, I mean, it's what jumped a couple of things. So the aim of the study of this work package and the aim of the study of this topic is, I mean, and this is quoted verbatim from the project, what are the symmetries, and especially quantum symmetries, and especially, I mean, that was mentioned exactly, isometry groups of graph system algebras, well, including those associated with higher rank graphs, so not restricting just, you know, to the basic examples. Now, as one knows, I mean, graph system algebras comprise a vast and absolutely enormous range of examples, and starting with absolutely simple ones like matrices, I mean, to something which are, I wouldn't say horrible, but quite complicated, and well, like Toeplitz algebra, I mean, on a sister algebraic level, quantum spheres both on the sister algebraic and on the level of, say, polynomials, also on the level of well, we can say quantum manifolds, so non-commutative manifolds on the level of spectral triplets. And it's any most beautiful example is just the SUQ2. So what I will try to say, and
Andrzej, if I might interrupt for just a second. I agree that the graph system algebras comprise a vast range of non-commutative algebras. However, this is a very special class. Okay, this is a very sort of one-dimensional line in this infinite dimensional ocean of C-star algebra.
Of course, yeah. That's. I mean, I'm not saying that they comprise. I mean, the meaning is that, of course, this is not everything, right? I mean, that's just an example and a beautiful example. But you see, I mean, this is an example. I mean, this is that I would say, you know, ranges, you know, from things that are, so to say, very simple to more and more complicated. And the thing is, I mean, you might agree that, you know, although the sister algebra description is quite beautiful, because, I mean, this is exactly, you know, the beautiful description of, you know, visualizing things as a graph. Then on the level, when you go to the level of, say, non-commutative manifold, this becomes, I mean, absolutely different and more difficult as it's not easy, you know, to translate, you know, the description in terms of generators for the that comes from the graph picture into something which gives you the description of a non-commutative manifold. So the question is, I mean, for instance, I mean, whenever you consider something as symmetries and quantum symmetries of this object, I mean, what are these? And I mean, the research, I mean, and the things, I mean, that I will mostly talk about are related to things understood as isometry groups. And this somehow relates to the previous talk also, because I mean, this is, I mean, the idea, you know, of studying symmetry groups is symmetry groups, I mean, with respect to something. And this is exactly, I mean, what's been said, I mean, symmetry groups with respect, for instance, to the Laplace operator, with respect to the Dirac operator. So this is the first part of my talk, would be something, what can we look at the symmetries with respect to an object? So what are the good objects, I mean, that we can actually, you know, restrict their symmetries? I mean, symmetry is not like something, you know, acting on an algebra or acting on some modules, but symmetries that also preserve something. So the idea, I mean, that we have classically, and that is exactly what was mentioned in the previous talk, is that the symmetries, for example, I mean, should preserve, I mean, like the group of unitaries, I mean, preserving, for instance, d plus d, d star, or preserving the Laplace operator. So this is the question, I mean, how to generalize it in the non-commutative world. One example, and I will come to that, is generalizing it with spectral triples and saying that, for instance, I mean, those quantum symmetries should commute, I mean, in a given sense, I mean, there should be sense given to that with a Dirac operator whenever you have a spectral triple. And I will make a comment on that, and I will propose something that, you know, came out of the research done recently with Ludwik Dąbrowski and Paweł Zalewski. And the good thing is that all those papers, I mean, they overlap mostly, I mean, also the part of the metric part of the project, but they propose one thing which is quite relevant for these symmetries. Namely, whenever you think about symmetries, I mean, that preserve something, that, for instance, preserve distance, you can, of course, think that they would preserve the Dirac operator. But there's one little catchy point in that. Namely, if you have classical Dirac operator, I mean, the Dirac operator, or the Laplace operator, I mean, general Laplace type operator, consists of several parts. So the Dirac operator has the part which is the first order differential operator, first order part, and the zero order part. And actually, you know, the part of the metric, the part giving you the metric, is contained in the thing that is this sort of alone part of the differential operator of first order. So the zero order part of the Dirac operator is relevant for several purposes, but it doesn't give you the information. It doesn't add anything to the metric part of the Dirac operator. So now the question is, I mean, for example, if you consider something, you know, commuting with the Dirac operator, you, in this way, have basically no way, I mean, going non-commutatively, distinguishing between these parts. So what is the proposition? The proposition is to use something which, as we know, I mean, in the classical setup, and as we can show, I mean, in many examples in the non-commutative setup, just somehow singles out that part that gives you the metric. But it gives you the metric, I mean, it gives you the metric in a sense that it's more close not to the distances on the states, for instance, but closer to the picture of what we call a metric tensor. So this is the clue of the first result, I mean, obtained jointly with Ludwik Dąbrowski and Paweł Zalewski. And this is the construction of several functionals over summable spectral triples. The idea is quite simple. Whenever you have, say, desummable spectral triple, which, I mean, we assume some little bit more, I mean, desummability is one thing, I mean, regularity. Basically, what we assume that there exists a generalized calculus of pseudo-differential operators that's built from the algebra generated by the commutators of the Dirac operator with the algebra itself. Everything, of course, is represented on a Hilbert space. And the absolute value of the Dirac operator to some powers. Now, what we assume, I mean, that the regularity and finite summability amounts also to the existence of the trace on this algebra, which is the non-commutative residue. So basically, the assumptions are as assumed in the work by Kohn and Moscovici for the local index theorem. Now, having assumed that, we can construct several nice functionals, which we call spectral functionals, over the bimodules, over the module of differential one forms. And the most crucial, you know, for the this part that would go into these symmetries of the quantum symmetries is the metric functional. So the metric functional is very, very simple. You take two one forms, which are U and W. So these are something like you can imagine, I mean, finite linear sums of the elements in the algebra and commutators, so deal with the elements of the algebra. And you take the non-commutative residue of U, W, and the absolute value to the power minus D, where D is this dimension summability of the spectral triple. That's a fantastic, simple thing, in most cases computable, but what are the benefits of that? Well, classically, so the first thing, I mean, if you imagine that you start with a manifold, which is of dimension, I mean, here we have, for simplicity, the even dimension, then this is nothing else, this metric functional gives you nothing else but some numerical coefficient with 2 to the m, which is just the dimension of the fiber of the spinor band. The Vn minus 1 is the dimension of the sphere in n dimensions, so the n minus 1 dimensional sphere embedded in n dimensions, and just the integral of the metric tensor, usual metric tensor, because I mean, when we start with a Riemann spin manifold of dimension 2m, I mean, we have a metric, and this metric evaluated on the one forms V and W, say here V and W, and integrated over the manifold with respect to the usual volume. Now, this basically gives you the metric tensor. And now, you know, we somehow singled out of the Dirac operator by this metric functional, we singled out the piece of the Dirac operator which corresponds alone to the metric. Well, you can say that in the classical case is somehow special and somehow...
Sorry, Andrzej, let me interrupt you. When I look at this formula, could we do some sanity check? V, W, Vn minus 1 are what?
Vn minus 1 is the volume of a sphere in n dimensions.
So this is a number. And
yeah,
now...
there's a number. There's a numerical coefficient.
Okay,
so these two are numerical.
And V and W are what?
Oh, sorry. Yes. I'm using V. Sorry, it should have been U. I do apologize for that. So that should have been not V, but U here. Yeah. Sorry for that.
But these are what?
In the paper, I think we use curly V for that.
These are one forms, VW. Okay, so
yeah,
that's
VW
okay.
here are one forms.
Yeah.
This is sorry. Yeah, this is a numerical coefficients. I do.
Okay, and when you say that they are bilinear, you mean bilinear over what? Function algebra?
Yes, let me just, you know, go into that's mentioned below, right?
Okay. Okay. Thank you so much.
Yeah. So of course they are bilinear over the linear coefficients, so over the numbers, but there's a little bit, you know, linearity, and which I mentioned in point 3. I mean the properties. Now the first thing, I mean, what I was saying, that the classical case is a little bit degenerate. It simply means that if you add something to the Dirac operator, so for example, I add to the Dirac operator something which is called torsion, or add some connection when you make it when you somehow enhance the Dirac operator to the Dirac operator with a connection over some vector bundle that you tensor with the spinor bundle, then it doesn't actually play any role. But that's the classical case, and we don't actually know whether this is somehow true. I mean, in the non-commutative case, when the algebra is non-commutative, when you add something that doesn't necessarily commute with the elements of the algebra, and that's the case, I mean, that would influence, you know, the full part of the Dirac operator. But the point is, the zero part of the Dirac operator doesn't influence this metric functional. So out of this metric functional, what you actually really get the most crucial information about this. You can call it, in the classical terms, something like a principal symbol of the Dirac operator. So the properties, the first property, which is the most important, it doesn't really depend on any bounded perturbation of the classical Dirac operator, but you can also show it in a non-commutative way. So in a non-commutative case, if you have a Dirac operator for a desummable spectral triple, and you make any bounded perturbation of that, the formula that I had for this metric functional doesn't actually change. I mean, it gives you the same result. So any bounded perturbation of the Dirac operator doesn't change this metric functional. So what you're actually studying, you're not studying any, you know, class of, say, fluctuations of the Dirac operator. You're actually studying sort of principal symbol of the Dirac operator. Now, classically, it's very nice because, I mean, well, we had, for instance, I mean, that, okay, I mean, when you consider some symmetries of manifolds, I mean, you can use the Dirac operator, you can use the D plus D star for the sort of this Hodge-Dirac spectral triple. That's, you know, also the same here. You can use it, and the answer, this metric functional, is the same. So basically, this is the same object. So this metric functional, which way you compute it, I mean, classically, using the Hodge-Dirac or using the spin-Dirac operator, gives you the same. So this is an object that you can obtain in, so say, different ways, but it gives you the same information. So this is exactly like the metric tensor. So this is the natural corresponding idea, natural corresponding object for the non-commutative manifolds, for the non-commutative spectral triples, to give you the idea of what is a metric tensor. Now, the properties of linearity, the linearity over the algebra, are, of course, I mean, this functional gives you a number. So, I mean, it's not like sin infinity of m, even in the classical case, linear. But there are certain properties, I mean, related with the bimodule properties of the one forms. Namely, I mean, the one forms are not only a modular, but a bimodule. And these are the, I mean, assuming the dimensionality of spectral triple and regularity and all that, these are the properties. So basically, if you multiply the one form V from the left by B, this is the same as multiplying W from the right by B. This is the same as multiplying W from the right by B, and the other way around, I mean, multiplying V from the left by A is the same as multiplying W from the right by A. And this comes, actually, this is the property, comes from the property of the spectral triple. So dissummability, the property of the commutator of the absolute value of the Dirac operator with the elements from the algebra, so basically regularity, and the trace property of the non-commutative residue. So,
and here your script A is what? Smooth functions on your Riemannian manifold?
Yeah. So small a and small b, I mean, in the classical case, are smooth functions on a manifold. But in a non-commutative case, there would be the elements of the algebra
Of course, yes.
that enters the spectral triple.
Of course. So now I'm sorry, it's probably a very dummy question, but I don't see this looking at the formula above, because you have an integral and functions are integrated over the manifold. So how come you are linear over functions? I'm confused.
No. This is not, you know, that the functions come out of the functional. You see, the functions don't come out of the functional. So on the left-hand side, you have a number. On the right-hand side, you have number. The sort of linearity is within the function.
Ah, yes, of course.
You see?
Yes. Yeah, you're right. Okay. Yeah. Yeah. Thank you so much. Yeah.
Yeah.
Mhm.
But this is, I mean, actually a nice property. And
Mhm.
now, I mean, what we can propose, I mean, and this is for the symmetries, we can propose to use this functional as a definition. What are the quantum symmetries of the metric? So quantum symmetry of the metric tensor. And this is the proposition. This is the proposition, I mean, for the sort of, I wouldn't call it isometry, but say quantum symmetries of the metric of the non-commutative manifold and embedded, encoded in a spectral triple. So whenever you have a Hopf algebra coacting on the, actually on the, I mean, what we should assume, coacting on the algebra of differential forms. I mean, this could be done possibly a little bit lighter. So it should be, I mean, probably it should be sufficient to have it, the coaction on the bimodule of differential form, of differential one forms.
But what do you mean the Hopf algebra? Which one?
Well, sorry, a Hopf algebra. I mean, a given Hopf algebra. Sorry, I mean, this is the, so once you fix, so the point is, I mean, imagine that you have a Hopf algebra, so actually it should be a Hopf algebra, coacting on the algebra of differential forms. Then, I mean, this is, for instance, this is example for the right coaction. I mean, using this Wheeler notation, we
You
can
mean left
propose,
coaction. This
sorry?
is left coaction. You have -1, so it's left coaction.
Oh, sorry, left.
No, maybe. The
So
problem is that this G can.
Sorry. So I used the, I probably used the wrong indices here. So this is this is a typo, because I mean this should be right coaction. Yeah.
So this should be +1, not -1.
Yeah. This should be the right coaction. So +1 instead of, so U and W, of course, U -1, W -1. I mean, stay in the bimodule of one forms.
Mm-hmm.
Yes.
And U0 and W0 are in the Hopf algebra.
Yes.
Yeah.
Now,
because you evaluate still G on the one forms. So this is
okay,
the,
so
sorry,
it should be U0,
I was meaning right
W0,
coaction,
then
but
U1,
I,
W1. Okay.
Yeah. So,
Tomek, you had a question.
Yep.
You raised your hand. You had a question.
it was my objection to this. What is
Okay.
written here?
So we
To
have
the
same
notation.
object.
Sorry.
This is swapped,
Yeah.
and this is a right action, coaction.
Okay.
This is the right coaction. This is example for the right coaction.
Okay.
So, I mean, I first used left, and then I somehow switched to right, and didn't correct it. Anyway, so for the right coaction, this is a suggestion. This is a proposition of a definition. What would mean the quantum symmetry of the metric tensor for a finitely summable spectral triple? And it uses a certain functional over the one forms. Now, you can say, I mean, what is the difference between this and the definition of quantum isometry groups? So, for example, I mean, the natural conjecture, the natural assumption would be that for the equivariant spectral triple, like the spectral triple for the quantum SU2, the quantum symmetry will be just the SUQ2 Hopf algebra. Now, why I say this is the conjecture, I can tell you one thing. So, what are the quantum isometry groups? And there's been, you know, a lot of studies of quantum isometry group. I mean, due to Goswami, Bonwick, and many after that. So the definition is quite simple. So for the quantum isometry group, you have a spectral triple. so called here BHD, so algebra be represented on H, Dirac operator, and compact quantum group, which has a unitary representation on H, that commutes with D tensor identity of A. So it simply means that you have a coaction of this compact quantum group of H, which is compatible with the algebra representation, and the Dirac operator just, commutes with that. Now, one can check quite easily that if you use this definition of a quantum isometric group, so if you have this CQG, then it is the symmetry also of the spectral functional. Because, everything commutes with the Dirac operators. The action on the one forms is basically through the action on the elements of the algebra, and the commutator with D of this action, of this coaction, is trivial. So basically, this function, would have this property. However, it doesn't work the other way around. So if you would have something which is the symmetry of this metric tensor in this way, of this metric functional, it doesn't guarantee you that this will be the quantum isometric group. So it doesn't guarantee you that it will commute in this way with the Dirac operator. Why? Because the Dirac operator consists of several parts, and the metric functional basically singles out, well, the sort of part that plays a role in, well, classically you can call it as a principal symbol. So the part, which is responsible for this metric. So anything that bounded that you add to the Dirac operator that might not commute with the coaction of, so with the representation of this compact quantum group, well, would spoil the quantum isometric group, but not spoil the symmetry of this metric functional. So the question is, and this is one of the open problems, and one of the things, one of the projects, that somehow originated in this metric functional discovery, metric functional construction. Well, could possibly be that the symmetry, quantum symmetry of this metric functional is bigger than the quantum isometric group. So what is it? Can one, for example, say something whether this could be significantly larger? Because, it might not be actually a global symmetry. This symmetry might be in some sense also in a way local. So this is one question, one problem. And the second problem, braided quantum groups appeared as, well, first they appeared also as some symmetries of classical objects. They appear as symmetries, for instance, as quantum spheres. Generally, also, they appeared in the construction. I will have a slide and the reference of some graph system algebras. Now, it might be that there will be also something like quantum braided symmetries, quantum braided compact, quantum compact groups of these metric functions, for a very simple reason. If you look at it, basically you have right coaction on U and W. What you do here, you do some sort of non-trivial swapping of the tensor product. So that
Sorry,
might
Andrzej,
be.
in this definition, wouldn't you like to ask some universality property to call it the quantum symmetry? Typically, it's like the biggest Hopf algebra that, in some sense, that coacts. Then I would be happy with your article, the.
Yeah. So, of course, you see, the approach to that could be, we look for the biggest symmetry that satisfies that. That's true. So then it would be the Hopf algebra. But of course, I would say, what I would be at least happy in some examples would be to look at least, at a proof that either it can be bigger or it cannot be bigger than the quantum isometry group. So that's the
And Tomek has a question, but before that, I'm puzzled by the problem you are posing. So you are saying that if you look at this Goswami-Bhowmick quantum symmetry, it's the quantum isometry group. You say that it might be smaller because you are taking a quantum symmetry or the quantum symmetry of functional, right? Am I correct in thinking?
Yeah,
about
I mean, it might be bigger. Why? Because I mean, the quantum isometry group assumes a sort of more rigid condition of commuting with the Dirac operator. So here, I don't assume this condition. I assume only, the condition that certain functional, has certain property, has this property.
Yeah.
And this functional doesn't use the full Dirac operator, so to say.
Yeah. Okay.
It simply singles out the part of the Dirac operator that's somehow responsible for the metric.
Yeah, I've got you. Now, Tomek?
My question, or maybe comment, is about the existence of such universal objects.
Oh, of course.
It's very hard to prove the existence of this. And
can I ask
condition?
But let him finish. Ludwig, wait.
Okay. So sometimes if you add some additional functional, which has to be preserved by this action or coaction, the more you add to be preserved, the easier it is to prove that this universal construction exists.
Yeah.
If you are defining this object which is preserved as being this functional, so you are in the middle. You are in the middle of between conditions which guarantee existence because some functionals are preserved, and it's still this functional is this, as you said, inner linear with respect to exchange of this bimodal structure between one form and another. Okay. So the existence of the universal automorphism of such a structure is somewhere in the middle and makes this problem so difficult.
I agree. I agree that might be actually more difficult than proving the universal for quantum isometry groups. That's true. Yeah. This might be a challenge. Just showing it, or challenge, showing that it might not exist. I don't know. Yeah.
Now, Ludwig?
Yeah, well, it's on the same line, essentially. Even Goswami, Bhowmick, and we computed also some examples, standard model and other things. The difficulty is to find the largest of the universal terminal object in this stuff. And also, same thing should be done here. If you start with something smaller, it can be still. If you don't find this biggest one, that can be smaller than the isometric group of Goswami Bhowmick. But if you find it larger, if you find it universal, you have to find. Okay, there are also examples of situations when it doesn't exist, Bhowmick, Goswami. So same thing can happen also here. So if both exist, then you can compare them, which may be quite difficult.
Exactly. But I would be at least happy to compare them in some, so to say, good examples, right?
But wait, Ludwig, what do you mean there are cases when it doesn't exist? I'm confused.
Well, I can, for some spectral triples, it's can be shown that it doesn't exist. I think, as far as I remember,
this quantum
there is no universal. Yes, I think so.
Okay, so
the universal object.
So this means that such a spectral triple does not satisfy assumptions of Goswami-Bhowmick for the definition of.
Oh yes, of course. When it satisfies it exists and it's okay. Sure, yes.
Okay. So it actually proves, this is a counterexample. So it actually proves that the examples of Goswami-Bhowmick are non-vacuous. That you have to make them. Okay.
Yeah.
Okay. Go ahead, Andrzej.
Just one addition to that. So I mentioned that
could you come back to the previous page?
Yeah.
Because you went over previous. Yes, about braided quantum group.
Yeah.
So your functional is symmetric.
Mm-hmm.
What do you mean symmetric?
What is the symmetry of your metric tensor? Is it symmetric or
a priori for the non-commutative cases?
Not.
Not necessarily.
Yeah, so in this situation, you cannot expect any kind of braiding, any kind of switch of these two slots in this.
No, but I don't mean, you know, switching to slots.
So what is the source of this braiding here?
I mean, the braided would be the symmetry. I mean, if you look at it, I mean, so if you have the coaction, so if you have the coaction on you, right coaction on you, you get, say, well, I mean, in this notation would be, well, u minus 1, u0, you have the coaction on w, and w minus 1, w0, and then you somehow, you need to swap the tensor product, I mean, to have the functional on the one forms. So you need to pass a one form through the element of the algebra, and that might result of the Hopf algebra, and this basically there's a crossing in the tensor products, and that might lead to, and then there might be, you know, some sort of origin for the braiding.
But what would guarantee the existence of such a swap?
Oh no, nothing. I mean, not that. I mean, I'm not saying that it exists. I'm saying that there is a possibility that the symmetries might not be actually compact quantum groups or quantum groups, compact quantum groups, but might be braided quantum groups, or might be. I mean, just exactly. I mean, it has been shown by people in Warsaw that quantum spheres, I mean, have also braided quantum group.
You mean Sultan, right?
Yeah, exactly. Sultan Kasprzak, yeah.
Yes, but my question was, what is the relation between braiding on the level of the quantum group of symmetries and symmetries of this bilinear functional? If it's not symmetry, if it's not somehow braided symmetry,
you see, I mean, I don't see. I mean, what I'm saying now, I mean, this is, you know, this is just there's not a question to which I have an answer. This is just a sort of a intuition that, well, intuition, or just a question that braided quantum groups, braided compact quantum groups appear as symmetries of, for example, I mean, quantum spheres. So it might be natural that they will appear here in this case, especially, I mean, they appear in the symmetries of things that when you take certain functional, like KMS functional over some algebra.
Yes, so
I mean, here you don't take a KMS functional, but you take certain functional, well, not over the algebra, but over a construct over the algebra, which are the one forms.
So the classical symmetry group could be related to the fact that your metric tensor is symmetric in a sense.
No. Why? No, I'm not saying that the symmetry. I mean, okay, I understand what you mean. I mean, possibly, possibly.
Stabilizing this functional, it would be so.
Yeah. Okay. Now I get your point.
Okay.
The idea might be, and it might be also related to the fact that in all the algebraic definitions of the metric that appear in many approaches, the algebraic definitions of the metric sometimes, of course, don't use the symmetry of the metric, but some sort of a braiding for the metric, like the symmetry. That's what you mean, Tomek.
No. My point was different. If your idea is to relate this braided structure on the group of symmetry with the symmetry of your metric as a function, bilinear functional of type of KMS, or maybe some modular automorphism, swapping these factors, then if this works, in the classical situation, the fact that the symmetry group or isometry group of the classical metric is a classical group would be a consequence of this relation between commutativity of this Hopf algebra and symmetry of this scalar product.
Yes.
Okay.
That's then I agree with what you said. Yeah.
Okay, let's move on.
Okay, yeah. So one just very short remark. I mean, what I mentioned is that in all the examples, and this we also had in the previous talks. I mean, you assume certain form of a Dirac operator for the spectral triple, and now the question is usually, I mean, this is the definition of the Dirac operator incorporates the metric, and the definition of the metric. I mean, understood as say distances on the states and something like that. But the question is, I mean, are we really getting the good Dirac operator? And one of the things, I mean, for instance, for the SUQ2 example of a spectral triple, I mean, a sort of a side thing was to show that this is really that the Dirac operator considered there is a good Dirac operator, means that it's torsion free. And this is a sort of a side result which I want to just mention. I mean, it maybe has nothing to do with the symmetries, but it tells you, that the symmetries of the SUQ2 with respect to the Dirac operator make sense in a way, because this Dirac operator is really torsion free. So it's really corresponding to what we consider as a Dirac operator without any additions. Now, I mean, this is just the reference. I mean, that the braided quantum symmetries of appear in graph Sitarz algebra. This is so to say were a reference to work out of the project, but anyway.
But these are not sister algebra. These are C lower star algebras. Your star has dropped.
The middle.
Yeah.
I mean, the top one. I mean, the bottom one is like
That's
that.
not the usual sister algebra. It's a lower star algebra.
Now, I want to report very shortly on a project together with Carla, who's in audience. And this corresponds, to something on a graphs, which is of some different aspect of graphs, namely graphs on rooted trees, and the relation between the paths on rooted trees to fractals, which is just, a very interesting topic in itself. And interesting topic, I mean, in relation to what was said just a while ago. So when you have a tree, so something like a rooted tree, so an infinite graph, basically, I mean, with vertices and edges, that each vertex has a couple of edges coming out of it, and so on, basically to infinity. You can introduce on this set of infinite paths starting in a root an ultrametric metric. Ultrametric means it doesn't satisfy the usual triangle inequality. It satisfies the inequality with the maximum on the right hand side. So not the sum, but the maximum. And you have an example of a very nice spectral triple, which is called Pearson-Belisard. Yeah, sorry. Thanks, Piotr, for the correcting.
So which one do you want, V or A?
A, of course. I mean, because I wanted to say the fractal set of something, but then I
and also what do you mean by if infinite paths?
Yeah. Now the results. I mean, the temporal results. I mean, what we want to do, and this is a report on a project which is in progress. We want to just check what is this metric functional and what are the spectral functional, but in particular the metric and then the torsion functional for this Pearson-Belisard or a variation of the spectral triple. And so far, an interesting result is that, I mean, the spectral dimension of this object, I mean, comes out sort of crazy. It consists of, I mean, the real part of the spectral dimension consists of a point which corresponds to the fractal dimension of the set of infinite paths, 0. And then there's a continuum spectrum in this spectral dimension of all points less or equal -1. So now, I mean, the next step in this project is the considering what's the metric functional. Well, there will be one more, and I will also mention about the other functional and tell something more about it. And considering, I mean, what's the quantum symmetry with respect, I mean, basically, I mean, also to this Dirac operator, but what's the quantum symmetry of the functional, of the metric functional? Because, I mean, the spectral symmetry of the Dirac operator, I mean, is one thing, but the Dirac operator, again, you know, this, you know, tells you only part of the information of the metric. I mean, now, sorry, I mean, yeah, this is just, you know, the picture. I mean, how this is actually, you know, an example of what's a binary tree. I mean, of course, the finite part of that.
Wait, isn't it the Christmas tree? Isn't it a Christmas tree?
It's a decorated Christmas tree.
Okay.
Because you can see some red and yellow, and green decorations on this Christmas tree. You can see two paths, both starting in the root. I mean, one is, I mean, the blue path, blue dot is the common. I mean, then you have the path which you can call the zero path. I mean, corresponds to the zero in the fractal 7. If this is, you know, the typical, if it goes to infinity, this is fractal set corresponding to the Kant. This gives the rooted tree correspond to the Cantor set. The algebra are the Lipschitz functions with this ultrametric. The Hilbert space are the square summable functions over the set of vertices times C2. The representation of the algebra is some diagonal representation. I mean, when you take, basically you take the function on the tau plus would be like sort of a path going here. I mean, looking at this tree to the left, maximum to the left, taking only left turn at each vertex. Tau minus would be taking the right turn at each vertex, starting with some vertex. And the Dirac operator is just, you know, some very nice function. Alpha is some weight to the power of degree of the vertex. Sigma 1 is the polymetrics acting on this square summable function over the vertices. So the question here for this example, and this is example rated not with graphs, system algebra, but with graphs, is something, what is the symmetry in terms of the metric constructed on this, on that. So this is something like work in progress work that actually started. Now I want to very shortly say about another aspect of graphs, which is just usual graph and which is the work in progress I have with a student, and which is very, very simple. Namely, there is a very nice, I mean, assume just a graph, a finite graph, for instance. And I mean, there are two approaches to graphs. One is just you give a sort of adjacency metrics on a graph, but there's something which is called incidence metrics of a graph. And this is very easy. So you consider the set of vertices and set of edges for a given graph. And then you construct a rectangular matrix, which is the matrix, I mean, of the size number of vertices times number of edges. And you just fill this matrix with zeros and ones. Just, I mean, this is the recipe. I mean, Iij is 1 if the edge j starts at I, so at the vertex I, and -1 if it's edge j, it should be edge I starts at j. So sorry, I mean, this is a typo. Edge I starts at j, or 0 otherwise. And then this is a rectangular matrix. So this rectangular matrix, I mean, doesn't give you anything, you know, that you can easily manipulate. But with this rectangular matrix, you can create two very nice square matrices. And one is I transpose, and the other is, of course, the other way around. So I transpose I. So one has one is the size of the square matrix with the size of vertices, the other edges. And this is usually considered.
Sorry, Andrzej, I believe it's written correctly. edge J ends at I and end J.
Oh, sorry. This is correctly. Yeah, one is ends, the other starts. I mean, I've read both starts, and this was
this is correct. I'm sorry.
Yeah, this is correct.
More than happy to correct it. But it's correct.
You're right. No need to correct. I mean, I was just somehow somehow reading it. This is you look at it and you read different.
Yeah, of course.
Yeah. Sorry. So one is called odd and even Laplacian. I mean, this is something like the typical literature. Now the question that we are, and this is the work in progress that I started actually a couple of months ago with a student who's actually in a master program only. So using this data, I mean, this Laplacians, I mean, what is the spectral triple? And we have a very nice idea because, I mean, if you look at it, I mean, if you look at this Laplacians, I mean, this looks like Laplacians that you have associated with the differential forms. So something like with the Hodge-Dirac Laplace operator. So, on the different, so Laplace operator, not only on the functions, but also on the differential forms. So there's a way, that we develop to go towards the spectral triple. And then once one has the spectral triple, one can start, to understand what are the isometries. In the sense, I mean, here it would be rather more appropriate, I mean, using the language of Goswami, so quantum symmetries, quantum isometries of this object. So of this graph in the way of spectral triple isometries. So this is the project I have with a student. And the final thing, I want to report on two results by Alex Kirvasitu. I think he's not in the audience at the moment. So,
but he's in the network.
He's in the network, and that's the reason, I mean, I asked him which of the papers, I mean, are most fitted. So I will just quote the results which are already on archive, and one is, as far as I know, already accepted in the Journal of Non-Commutative Geometry, I mean, he told me. So the first is about the quantum group co-products and university under scalar extension. And this is just about, the simple question, I mean, about which products in some category of Hopf algebras gives you, something which is finite dimensional. And basically, this is the simple results. I mean, I thought, he might be in the audience. He might tell you a little bit more. And the second result is about some general results on quantum symmetries. So actions of compact groups, classical and quantum, on Banach spaces, and those properties. I mean, I signaled out the two properties that the unitary representation of compact quantum group induces continuum action on a C-star algebra of bounded operators, if and only if it has finitely many isotopic components. And then compact quantum group is finite if its continuous action on C-star algebra leads to continuous action on the multiplier algebras on von Neumann envelopes. So these are just, just flashes of those results from the work of Alex, which fall into this general topic of quantum symmetries. So that's all for the review of what's being done, what has been done, what's being done, and what is to be done in this part of the project.
Thank you very much, Andrzej. I have a question to Ania Kula. You just visited Buffalo. Did you have chance to discuss with Alex Kirvasitu this stuff?
Yes, not exactly what Andrzej was talking about. We discussed something different, namely that there is a specific quantum group coming from Voronowicz construction, and it seems to us it might be an example of a so-called Azumaya Loci or locus, So this is what we talked about. This is still in progress,
Mhm.
and nothing in any kind of final written form. But yeah, this is something we discussed there.
Okay, this is great. Okay, since we are quite behind the schedule,